All right, so we are recording. We are going to get started, even though maybe half the class is here right now. Okay, maybe a little more than half. I am not going to wait, so we are going to start with where we left off from Monday, and I did a little bit of change here. That's why we're in the GitHub screen. So we're going to go back to the module, which now should have the updates. I will show you what the update is, okay, just so that you know the revision. So the revision has to do with stating that you can only have one member. You cannot have duplicate members in a set. Okay, so that's something that I talked about on Monday, but it is now officially in the note here. Let me see, where did I put that? Oh, these are examples. So I probably put it up here. Right here. Okay, so membership in a set must be unique. This means no two elements in a set can be equal or can equal each other. Is that okay? Does everybody understand the meaning of the sentence that I just highlighted? Okay, so that's the only change. Okay, that's the only change that I made. So if you have printed, the document, you can either print it again if you don't mind, just spending a little bit more money, or you can just kind of add this sentence to the one that you have printed already. I just want to make it clear, okay, what changes I have made. If you go to the GitHub page, that would also show you all the changes, recent ones at least, so you can actually also, check that for updates. All right, so first thing first, do we have any questions about the topics that we have kind of talked about on Monday? Any questions about the notations? Okay, no questions about the notations. Any question about concepts? No question about concepts. All right, so if that is the case, we are just going to be moving on. Question? Yeah, go ahead. Um, okay, so yeah, okay. So we can restart from cardinality. So would that cover all the topics? Or is it a topic before the cardinality? Yeah, we'll talk about that today. Yeah, yeah. Okay. All right. Um, okay, so let's start with that because I definitely did not talk about those two, on Monday. So on Monday we kind of stopped, when we talked about cardinality, and I made a few, kind of interesting comments about, how, okay, I made a comment of the cardinality of natural numbers is actually the same as the cardinality of integers. Okay, which is really awkward. Okay, because one is actually the proper subset of the other one. Okay, in other words, in this case, the set of all natural number is actually a proper subset of the set of all integers. In other words, every natural number is an integer, but we can find integers that are not natural numbers. Okay, so just by mentioning this, I'm actually trying to force you guys to think about what is the definition of a proper subset of, okay? Because that's something that we talked about on Monday. So do we have any questions about the assertion of this Boolean expression is actually true? Yep, integers. So in that are not natural numbers. Yep. At least one. All we need is just at least one. So that is true because if you think about integers, 5 is an integer, but it's also a natural number. But -6 is an integer, but it is not a natural number. So that means, just intuitively, we can figure out that if x is the set of natural number and y is the set of integers, it meets this requirement, but it also meets this requirement because -6, we only need one, right? So -6 is a integer, but it is not a natural number. Are we okay so far? Okay. Hmm? Say, uh, because we can define classes of of numbers. Yep, because real numbers is not in the same class as natural numbers, but integers are. So there are special properties about the entire class of set because they're equivalent to each other. So if we can prove certain properties of one particular set within that category, that applies to everything else in the same category. Yep. Yeah. Yep. Exactly. All right, so we are going back and continue with this notation here. So this notation is really just an abbreviation of this notation here. This is literally, okay, what you say is for all e in x, p of e is true. Okay, that's literally what it means. But it also expands to exactly the same thing as for every E in the entire universe, E is an element of X implies P of E. So these two statements are exactly the same. This is the long way of saying it. This is the more abbreviated way of saying it. Do we have any questions about this? Yep. hmm Okay, so when X is 1, Y is 0, and you're asking why X implies Y is a 0? Is that the question? Okay. There, I can offer a few different types of answers. Okay. The first answer, which is which seems to be authoritarian. Okay, but it really is the best answer because in mathematics it is all about definitions. Okay. So the first answer is that's how it is defined. Is the truth table. Okay. So what the case that you were talking about is this row here. And that's basically how it is defined. Is that okay? It, okay, so implication itself is an operator. It is not an action. So that's why there's the confusion is when we use implies in natural language, it is usually used as a verb, which means, okay, this is happening, and that's why that should also be happening. It is a verb. It's describing a causal relationship, in the natural use. But in mathematics, implication is an operator. Just like and is an operator. So when we use implies as an operator, we are not linking the first or the left hand side with the right hand side in a causal relationship. It is not an action, it is simply a relational kind of thing. We are relating the left hand side with the right hand side, and we ask the question, is that relating true or false? So is that helping to clarify? It is asking, is it relating using this truth table? Is it true? Is the implication true according to this table? So we kind of go back, to the definition, right? So the other way to look at implication is X is a sufficient condition for Y. So that's the other way to look at it. So if X is sufficient for Y, that means if X is true, Y should be true if the statement itself is true. Does that make sense? But if X is sufficient for Y, it does not say anything about what if X is false, because there can be other sufficient conditions. And that's why, when X is false, X being a sufficient condition for Y, when X is false, it simply means that we cannot make a conclusion, which also means, when X is false, the statement saying that X implies Y is still true. All right? Okay, go ahead. Uh-huh. So you mean here? So this is just a placeholder. Because in order to describe the syntax, I need a placeholder to specify, what is the element that we are talking about, what is the set that we are talking about, and what is the predicate that we are talking about. So if you think of it from the positional perspective, this is the element of, operator. So that means, whatever is on the left-hand side is specifying, it's the placeholder of an element, and then whatever is on the right-hand side is the placeholder for the set where the value may be an element of. And then the P is inside the parentheses, inside the outer parentheses over here with its own parenthesized parameter E. So that's just the syntax of saying, okay, this is the predicate that we are talking about. Yep. All right. So those are all good questions. Yes. 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 That is definitely not a tech thing. There are things that are very tech, okay, in this class, which means no one else look at it in that particular way, but the definition of implication is pretty universal. Yep. All right. Those are all very good questions. Any other questions? Oh, I can remember one thing that I can address. Okay, so the other day there was a question of if a student is asking a question, would the voice of the student be recorded in the lecture recording? So I can understand that is a valid concern. So this is your OBS. Okay, I know it looks kind of funky because it kind of gives you the infinite mirror thing, two parallel mirror. Okay, so I'm gonna shut up, and one of you guys can try to talk. You know, in a loud way. You can just say, I don't have a question. Okay, so I'm going to shut off. So this gives you an idea of how localized the mic is picking up because it is only about at the most an inch and a half from my mouth, okay? And you are much further away, okay? Do you guys know about how audio signal attenuates or decreases over distance? It is 1 over r squared, r being the distance. Okay, so that means if you are at twice the distance from my mouth, that would mean you're in my personal space, and I'll probably back up first. That would be very personal. Like it's like no, no, nobody should be that close to me. So if you are, let's say, 10 times, okay, the distance of my mouth from the mic, and you're 10 times that distance, you will still be in my personal space, but the signal would be 1/100th of my own voice. Is that making any sense? So that means unless you intentionally want your voice to be recorded and talk really, really loudly, it's not going to pick it up. Okay, that's just physics. So Okay, are we understanding that? So that means, if you want a question to be repeated, I have to repeat it because the mic cannot pick it up. Is that okay? All right. So I like to explain these things, because it is physics. Okay, it is just how things are because of the nature. All right. So we are getting back to for all e in x, p of e. That is really just a shorthand. Instead of having to write this, we just kind of have a shorthand like that. Okay. It's also easier to read for the most part. The other one is for the existential quantifier. Um, there exists E in X such that P of E is true. So that is an abbreviation of there exists an E in the entire universe such that E is an element of X and P of E is true. Okay, so the important part is this is an implication, this is a conjunction. Okay, so that is the main difference. So are we okay so far with those two um, shorthands? Believe there are some examples. Okay, so the example on the first one is for every I in Z, which is the set of all integers, I is an element of R. That quantified expression is true. Okay, because um, because E in Z implies excuse me, I in Z implies I in R itself is true. Are we good so far? Or do you guys want to expand on that statement? You don't need to expand on that statement? Okay, all right. Then we can move on to this particular example. Okay, so this example says there exists an I in Z as an integer such that I is greater than 0 and I is less than 0. So this entire quantified expression is false because you cannot find a single integer in the set of z. Well, okay, that's repetitive because when I said a single integer, it implies I is an element of z, such that it is greater than 0 and it is also at the same time less than 1. Are we doing okay so far? Okay, all right. So we talked about the BNF, for listing membership, and this is the BNF of a tuple. Okay, so the term that is being defined here is tuple, which from your perspective, depending on your programming language, you can think of a tuple as an array. You can think of a tuple as a list. Okay, so that kind of depends on the programming language and how it is usually called, and sometimes you can call it a vector as well. Okay, so for math people, it is called a vector. For C++ and Java programmers, it is called an array. But if you like to work with Python and JavaScript, sometimes it is called a list. But they're really the same thing. Okay, ordering is important, and you can have duplicate values within a tuple. Okay, so the concept is called a tuple, and we are looking at the notation in this case. Um, and the syntax is this. Okay, so this is the syntax. So let me see if you guys remember what the syntax means. And I will emphasize in this case that the parentheses, the outermost parentheses, those are actually bold-faced. The comma itself is also bold-faced, and everything, nothing else is bold-faced. Okay, so what does that mean? What does the square bracket mean? In other words, from here to here, what does the square bracket mean? Yep, that it is optional, which means you can have 0 or 1 occurrence. Okay. Um, what about the curly braces over here? They're not bold-faced. What do they do? Yep, it's for grouping. Exactly. So this way we can refer to a group of things and then we say something about it, right? So we have a little asterisk here that is not bold-faced right after the end brace. What does the asterisk mean? Hmm? Repeat any number of times, including 0. Okay, so including 0. Okay, very good. And what does italic means in this case? It is a placeholder. It's called a token, right? So that's exactly what um, is being represented here. So 1, 3 is called a tuple because it has a length of 2. Okay, we don't say cardinality when we look at a list. We just say the length. Um, all right. So the in this case, if this is x, then we can also say that x bracket 1, bracket 0 is 1 because we're using the indexing operator to access only one of the items in the list or array. Or we can also say x bracket 1, which is referring to element 1 of the tuple, has a value of 3 because we are using 0 as the orientation of the entire indexing scheme. Okay, are we doing okay so far in terms of the concept of a tuple? Okay, all right, very good. So in case you are okay, I can give you some actual code example just so that you know how this is mapping to a programming language that you know. So we'll start with C++ because C++ is the prerequisite of this class, and I'm thinking that you should know about this kind of stuff. So in C++, if I want to declare a variable, an array, I can do it something like this. Okay, so we can use x is fine, and then you use open and end square bracket to mean that okay, this is an array, but I'm not telling you the number of elements yet. But you can make it an initialized array. Okay, and in C++, the curly brace is also used for grouping. Okay, it's for scope control, but also for grouping. So in this particular case, I can say, 1, 3, like this. So now with this declaration, X becomes a two tuple where the first member or first element has a value of 1, and then the second element has a value of 3. It will be equivalent to what we see here. Are we good? In JavaScript, okay, which I kind of mentioned the other day. And for those of you who want to learn JavaScript, the syntax will be something like let x equals to, and you can define um, an array as a literal in JavaScript. So it is really quite handy to be able to do that in JavaScript. In your JavaScript, you don't need to have a semicolon to end something on the line, which can lead to a lot of confusion because that's my default is not to have a semicolon. So when I have to switch back to C++ or Java, I often get bitten by that one because if the compiler says you don't have a semicolon ending on this line, you have a problem. But in JavaScript, that semicolon is actually not needed. So are we good so far? I'm not a Python programmer, so I don't know how Python, um, what is the Python syntax for literal arrays? Does anyone know? Hmm? Okay, so okay, cool. Yeah. Okay, cool. So in Python, it's just parentheses. Okay. Does anyone know Perl in this class? Perl. So Perl is, I'm not gonna say it. Okay, Perl is different. It depends on whether you're referring to the actual literal of the array or a reference to the array. It's different. The syntax is slightly different. So we're not going to go there. Not going to go there. All right. So the idea of talking about the concept of a tuple is because tuple is necessary to define the next operator. This is the next operator. I'm putting my mouse pointer over or right under the operator itself. It looks like multiplication, okay? It is called the Cartesian product. Okay, so the full name is called the Cartesian product, which is all kind of spelled out here. For those of you who have taken linear algebra, you can call this cross product. Okay, it is the same thing, almost the same thing as a cross product with a little bit of difference. So it is kind of like a cross product. Okay, so now we take a look at the definition and we try to kind of reapply what we have learned and you'll see how this how see this is defined. So the full sentence is saying This is the definition of this particular symbol. So for all we know, what is in the rectangle here is just some funky symbol, okay? Because we're just defining the operator in terms of what it does. The actual definition itself starts with for all E, for all F, okay? So these are not um, scope limited. In other words, I don't say for E in something, for F in something. I'm just saying for everything in the universe E, for everything in the universe F, which can or cannot be the same, okay, both. EF as a two tuple is inside this set. So that tells you that Cartesian product returns a set of some kind, okay? So EF as a two tuple is in the Cartesian product of x, y, if and only if E is in X and F is in Y. That is the definition. This particular statement that is quantified is always true because it is the definition. And because it is always true, that means that if and only if is always true here. So that means, it defines, what it actually defines the membership of X and Y. And then we're looking at the Cartesian product. Yes, it is if and only if because of this symbol. It is the same thing as equivalence. Yep. But it is also called if and only if. They are exactly the same thing. But very good. Okay, I'm glad that you noticed that we have not talked about if and only if, but that's actually also called if and only if. In some of your math classes, they would do an abbreviation because to spell out if and only if is typing a lot of words, and mathematicians do not like verbosity. So what do they use instead of if and only if when they don't use a symbol? Yep, IFF. Yep. So IFF and this symbol are exactly the same thing. Okay. Yes. Um, Equivalence is equal to, but only applicable to Boolean values. Because equal to is applicable to any two values, right? So equal to, you can, if you know that you're dealing with Boolean, you can substitute if and only if with a single equal to in most contexts. Yep. But we look at it as an operator instead of a comparison. So we look at it as a Boolean operator. But you are correct. It is doing the same thing as quote unquote equal to. So, yes, go ahead. Reading, uh huh, uh huh, yep, yep, whatever that thing is. Yep, we just call it, yep, yep, yes, correct. But it is the definition. So that means this statement, which is quantified, is guaranteed true because it is the definition. So that means we are using this particular quantified expression to define the symbol, which is Cartesian product in this case. Okay. It is the Cartesian product between x and y. Yep. All right. Which is also explained here. X cross y is called the Cartesian product of the sets x and y. Yep. Nope. They do not need to match dimensions. Okay. So let's go ahead and use an example. Okay. So from the questions that we are getting, I think it's a good time to make use of an example. So I'm just kind of thinking about whether I want to use my editor or whether I want to use the whiteboard for this. I'm gonna use the editor. Okay. So give me a second, get to the right. Okay. This is from my other class, so we're gonna get a new uh, document here. All right. So we're gonna define X. Okay. This is the definition of X. X is the set that has A, B in it. and Y is another set. It has 1, 2, and 3 in it. Okay, so that's just by definition. Okay, no particular reason, just for this example. Are we good? Are we, are we okay? All right. So now we are evaluating. Okay, let me just kind of resize this a little bit so we can actually see a part of the definition here. So we are now evaluating a bunch of pairs of E and F. Okay, so one of the obvious one is, what if E is the value A, and what if F is the value, say, 3? Okay, so in that case, okay, so we have to look at the whole thing. So in that case, what is E in X? Because I cannot really use the special looking operator here, so I have to spell it out, right? So E in X it can either be true or false. Is it true in this case? It is true, okay? What about F in Y? Is that true or false? It is also true. So what is true if and only if true according to the truth table? It is also true. Okay, now that is a sentence that has a lot of true in it. Let me say that one more time. What is the value of true if and only if true by the truth table of equivalence? The answer is it is true. Is that okay so far? Okay. So if the right hand side is true, that means by this if and only if, the left hand side has to be true. So this means this this is if and only if. Okay, I take it back. I should not be using if and only if here. I should be using and, because this is the and operator. So true and true is true, and that tells me that EF in this case, which is A3, is also in the funky thing that we're trying to define, which is the Cartesian product between X and Y. I'm using a lowercase x to approximate the operator because it is the closest that I can get. Mm, it doesn't have to. Okay, so let's look at another example. Okay, so now we have established one member, in the result of the Cartesian product between x and y. In other words, we know for sure that the A3 two tuple is an element of the Cartesian product. Okay, so now what do is we look at another one. Okay, so in another test case, we say, okay, what about the case when E is A and F is 2? Okay, so in this case, E is in X is true, F is in Y is also true. So now we also have true and true, okay, based on this and over here, which means in this case, A2 is also in X Cartesian product with Y. Is that okay? All right. So we'll take a look at some funky cases now. Okay. What if E is the same as A? Okay, but F is tach. Can F be tach? It can, because this quantifier says for every F in the entire universe. I'm still in the universe as we speak. Okay, so even when if I die and people are listening to the lecture at that time of the recording, I'm still alive. Okay, yes, I'm talking about some existential stuff here, but you can ignore that part. Okay, so F is tach. So now we look at the expressions. E in X is true, F in Y is what? Okay, so that means your true and false is false, but the if and only if itself is true. So that means a tach, oops, a tach in X Cartesian product with Y is false. And I will put parentheses around it. So I'm excluding a potential two tuple to be a member of the Cartesian product. Are we doing okay so far? Do you see how this works? Okay. So this is really kind of important because I'm using the very same notation that we have been talking about in this class to define additional notations. Okay. There are other ways to define operators, okay, using a more quote unquote intuitive way, but I choose to do it in a very structured way using just logic and symbols because that is for the most part, how mathematics and computer science works. It's a lot of symbols, and we have to go by the definition of things. Are we good so far? So, given this particular example, what would be the full membership of the entire set? Okay, so if we look at x times y, or Cartesian product, if we know it's a set, and we know the set has a bunch of two tuples, so we already know that A3 is there, A2 is there, so I think A1 is going to be there, A2 is going to be there, A3 is going to be there, B1 is going to be there, B2 is going to be there, and then B3 will also be there. That would be the full membership of the Cartesian product between the left-hand side, which is a set of AB, and the right-hand side, which is the set of 1, 2, and 3. Is that okay? But do you see why I kind of named this, as it's kind of like a cross product? So if you have taken linear algebra, this should remind you of a cross product, even though it's not exactly a cross product, okay? It's kind of like a concatenation thing combined with a cross product. Are we doing okay so far? Yep, go ahead. Yeah, because in the actual cross product, there's a each result. Okay, in the resulting matrix, okay, the position matters, right? But there's no positioning here, but it has the same effect as a cross product in terms of if you have a vector of length 2 multiplying cross product, with a um, vector of length 3, you end up with 6 things in the matrix, in the resulting matrix. So from that perspective, it feels a little bit like a cross product. You mean oh, okay, to name the result as Z? Yeah, we can do that. So we can always define, Z as a new set, and it is just that. No, because it's still a set. Within a set, there's no ordering. So there's no way you can use indexing to pinpoint a particular element. Yep. Yep. Go ahead. Yes. So the cross product, anything cross product with an empty set is an empty set, or you can also say empty set cross product or Cartesian product with anything is also guaranteed to be an empty set. Yep, that is correct. Okay. Yep. All right. So that the question is whether this is a single element in x times y, right? In the Cartesian product of Cartesian, Cartesian product of x and y. The answer is yes. It is considered to be a element in that set. Even though it's a composite, it is still considered just an element. So in this case, I'll address your question. So in this case, the cardinality of the Cartesian product between x and y is 6. There are 6 elements in the Cartesian product in this specific case. Okay, go ahead. No, because it is a set of arrays, which is not the same as an array of an array. Because when we talk about a set of arrays, that means the elements within the set do not have an index. We cannot say the first element, the second element, or the third element because there's no ordering within a set. Okay. Yep. Go ahead. Well, it is okay. Let's try something even more extreme. Okay. So I'm going to redefine everything. I'm gonna scroll all of this out of the screen so we don't get confused, and then just visually, kind of divide everything. So this is a different example altogether. Okay. So we define x to only have a single element of one. We define y to be a set with only the same thing here. So x and y are essentially the same. So in this case, the Cartesian product between x and y is really just this. And that's it. Because what is the other way to say this is the Cartesian product between x and y has to be a tuple. In that two tuple, the first item has to come from x, the second item has to come from y. But that definition is not the full definition because that particular definition does not exclude, it doesn't say that it cannot miss certain things. It also cannot say that it cannot contain extra things. So that's why the if and only if earlier is important because it excludes other things to be in the Cartesian product, but it also makes sure that everything that should be in the Cartesian product are in the Cartesian product. All right. Any other questions? Yep. Can I go up? Okay, sure. All right, let's check out what's going to happen in that case, okay? Because what we are really trying to do is to confirm the membership or the lack of membership, okay? So that's what we're trying to confirm. So we'll say, okay, E is what again? 1, and then F is 8. Okay. So in this particular definition, this is how X and Y are defined. Okay, we're keeping that definition. So that means E in X is false, F in Y is also false. So false and false is false. So false if and only if the other side also has to be false. So that means the two tuple 1a is in the Cartesian product of x and y is false, which means it is not in the Cartesian product. Hmm. Um, it has to be in that order. Say that one more time, please. No, they do not. So A1 as a two tuple is distinct from 1A as a two tuple because in a tuple, ordering matters. Okay. Yep. So ordering matters within the two tuple, and inside the two tuple, you can have duplicate values. Are we still doing okay so far in terms of the concept of the Cartesian product and how everything inside the Cartesian product is a two tuple? So those two concepts are good. All right. So we can now go back to this one here. So now if I give you two sets, okay, and I say that they are the same, so now we are looking at the comparison of sets, okay, are they the same set? This is true. Set x is the same as set y if and only if x is a subset of y and y is a subset of x. Okay? Everything in x can be found in y, and everything in y can also be found in x. So that goes back to an earlier observation that is super weird because now we can say the set of integers equals to the set of natural numbers is false. How do we know it's false? Because one is the proper subset of the other one, and the other one is not a proper subset of the first one. So we know they're not the same. And yet, we say that the cardinality are the same. Okay? And there's more, okay? There's more because we also know that n, or the set of natural number, is a proper subset of the set of all integers. So this is true, okay? They are not the same, okay? We'll put a not equal here, and just to make it easier to read. We know this is true, okay, by definition. We also know this is also true based on what we understand about natural numbers and integers, okay? So how can they all be true at the same time, okay? So that's something that I can explain only after we talk about functions, okay? Because it has to do with mapping. All right, so let's go through some of the examples, okay? And we'll take a look at list. Oh, okay, this is a good one. The following is a list of all the subsets of A, B, C as a set. So it includes the empty set itself, the set with only A in it, the set with only B in it, the set with only C in it, the set with AB in it, the set with AC in it, the set with BC in it, and the set ABC itself. Okay, so there are 8 of them. Okay, so if I were to, so this is called a power set symbol. This symbol here is called a power set. So the power set of a set S is basically the set of all the subsets of S in this case. So that means the power set of ABC has all of these as elements. Yep, but they're considered to be the same. So the set of CBA and the set of ABC are the same. Okay, let's think about this. Okay, let's think about this a little bit. Okay, we define x equals y if they're both sets, if and only if x is a subset of y and y is a subset of x. Okay, so this is definitional and definitive, and we talked about this earlier, right? So now the question is, okay, if we think about the two sets that you just mentioned, okay, the set with say 1, 2, 3 in it, and the set with 2, 1, 3 in it, okay? Can I say the first set is a subset of the second one? In other words, is everything in the first set found in the second set? Okay. Can I establish the other way around? Is this also a subset of 1, 2, 3? Well, then we have met the definitive, the definition of how two sets can be seen to be the same. So that means they're really the same. So that means I can show this set as ABC. I can show it as BAC. I can show it as BCA. There are 6 possible ways to list it, but they are really just the same thing. They're basically quote unquote aliases of the same set. Yep, that is correct. Yep. No two sets can be proper subsets of each other. Because in order to be a proper subset, there has to be one thing that is missing in one and is present in the other one. But it cannot be mutual. Yep. It's not possible to be mutual. Okay, very good. So the next statement here is saying whatever set X, excuse me, whatever S is as a set, the power set of S has the cardinality of the power set of S is 2 to the power of the cardinality of S itself. Okay, so you look at this, little equation here, okay, which I claim is true, okay, what are you going to do? What is the first thing that you're going to do when I say, oh, this equality holds? Okay, let me move the mouse pointer to talk about the actual equality that I'm talking about. So I'm talking about this equality. Your text says in class that this equality holds. So what are you going to do about my statement? If you just write it down and accept it as truth, then it's okay. It's better than not writing it down. Okay, but what I really think you should do, okay, is to question it. Okay, is to say, um, okay, first of all, I don't know why. Okay, two, um, do we have an example where that statement, that equality is true? Yes, we have an example. Okay, we have an example of the set of ABC. Okay, how many elements are in the set of A, B, C? Three. Okay, so according to this statement, it should have 2 to the power of 3, which is 8 elements in the power set. In other words, it should be able to generate 8 subsets. Now, I did not say proper, okay, just subsets. And this is the list. Okay, that's this is the enumeration, which means I'm listing every single possible subset of the set ABC. So now you go like, okay, that seems to make sense. Okay, the example matches the statement. So the next question that should pop up in your head is, but why? Okay, yep, hmm exactly. Exactly. So every element is representing two branches in the decision tree, and the decision tree has three levels. Okay, so this is me, kind of giving you a graphical explanation. So this is something that you can also kind of put in your notes. Okay, all right. So we are looking at this as a tree, and that's also the reason why CISP 430 is a co-requisite of CISP 440 because you may not be learning about trees yet in 430, but you will. So the two classes are kind of intertwined a little bit because we talk about similar concepts. One from the perspective of algorithms and C++ code, the other one from the perspective of math and really just the abstract construct of the concept. Okay. So from the perspective of a graph, okay, this is decision point zero, and I just need to know whether A is in the set or not. Okay, so you go like, yep, A is in whatever set we are creating, and the other one is A is not an element in that set. We're choosing whether to include A in the resulting set or not. Is that okay? So do we all agree as far as element A is concerned, it can either be or not be in the resulting set? Because we are not in a quantum mechanics class, so it cannot in a superposition of both being in and not being in at the same time. And I highly encourage everybody to take at least a few classes in quantum mechanics if you can, because quantum computing is the future. You can quote me 10 years from now when you become billionaires. The AI stuff that we are talking about now is not quote unquote the future. Quantum computing really is the future. So if you have an opportunity to take a quantum mechanics class, please do. Okay, I think it is going to open up possibilities for you. Okay, so now we look at the second decision point, and we go like, okay, let's think about whether B is in the set or not. Okay, so the two branches is like, okay, B is in the set, B is not in the set, B is in the set, B is not in the set. Okay, so I know people in the back may have some problem, looking at the tree, but I think you get the idea. Are we good so far? Okay. So now we have three elements, right? Because the set has A, B, and C in it. So now we make the third decision. So now we have in, not in, not in, not in. Okay, so I'm even going to comment all of these things here. In, not in. in, not in, in, and not in. There we go. So now at the leaf, okay, of the whole tree, so a leaf of a tree is the terminal, okay? It is basically, when we do not branch any further, okay, those are called leaf nodes or just leaves. So if you look at this particular leaf, we go like, okay, A is in, B is in, C is in. So we have this set here. Is that a subset of A, B, C? Yep. Okay. We'll randomly pick another one. Okay. We'll just randomly pick this particular node over here. So how do we get to this node? A is not in, B is in, and C is not in. So this node here is representing just the set with B in it. Is that a subset of the set ABC? Yep. So if you go all the way to the bottom, and know people in the back, are having problems seeing the bottom one, but the bottom one is basically saying A is not in, B is not in, C is also not in. So what is that leaf representing? The empty set. And is the empty set a subset of another set? I don't even care which one. Yep, because the empty set is a subset of every set there is. Is that okay? So I think if you look at it from the perspective of a decision tree, it becomes more obvious why um, the cardinality of the subsets that can be generated by a particular set is 2 to the power of the cardinality of the set itself. Because each member can either be there or not be there. There are only two choices. All right. Are we doing okay so far? All right. So I'm not going to use the concept of power set too much in this class. So, it's okay, but, it's a concept that you should know, but we are not using it too much in this class. And also remember, this class is for the most part really just introducing the ABCs in your upper division class at a 4-year university. Okay, so there, I can think of at least two classes that most computer science people have to take. One class is called the analysis of algorithms. And typically, at a 4-year university, they will say introduction to the analysis of algorithms. Every time the academics say something is fundamental or introduction to, it's not. Okay, so typically that is a really heavy math class, and we are only introducing the symbols and the definitions to facilitate the upper division class in this case. Okay, so the other class, because I mentioned two, right? So the other class is called computational theory, which is sometimes it's also called automata. You know, and it is based on Alan Turing's math, to model computers. So who's Alan Turing? Yep, he is considered to be the modern day father of computer science. Okay, so his name is Alan Turing. There is a movie about him, and what is the name of that movie? Imitation Game. Yep, Imitation Game. Um, it is kind of important. I mean, historically, his contribution is to look at computers, but from a mathematical perspective. So he, in the late 40s or the early 50s, he already knew what is possible and what is not possible with computers that we know today. He did not know about quantum computers, so his theory cannot be extended to include quantum computers. But for all the other deterministic computers that we have these days, all the theories of what is possible and what is not possible, he already had theories back in the late 40s or the early 50s. And typically, a computer science program at a 4-year university has a class to talk about, his mathematics, on the modeling of computational hardware. So that's also a math-heavy class. All right, so I really just want to establish the context of this class, okay? Because by itself, this class is quote unquote a capstone class at this level, which means we don't have any other classes in the computer science program that depends on this class. That's because we are setting up the groundwork for the other classes that you have to take as upper division classes once you transfer to a 4-year university, which means this class is actually, in some ways, more important than CISP 400 or 360 because those are kind of like classes to get you up to a certain point, and then after a certain point, the other computer science classes are not about programming anymore. It is all about theory and math. Unless you go to one of those UCs where you can bypass the really hard classes and instead you take a class in VR fashion design and stuff like that. I'm not going to name the university, but there are such universities where you can substitute or the program gives you enough flexibility so you can bypass all the hard classes and you take classes in UI UX stuff. You take classes in as I mentioned fashion design in the VR space. And by the way, it's pretty much dead by now. Okay, yeah, Meta, okay, Mark Zuckerberg, pretty much you pull all the resources from the VR projects to the AI project now. Yep. So, but I will leave it up to you guys, okay, to decide how you want to design your own, computer science curriculum, when you transfer to a 4-year university. All righty. So, I mean, yes, go ahead. It's usually a graduate program. The reason why quantum computing is usually a graduate program is because in order to get into quantum computing, you need more math classes. So linear algebra, differential equations, they're not enough to give you the foundational math to understand quantum computing. There's a special branch of math, that links to quantum computing. It's basically a combination of complex numbers and linear algebra. Okay, so when you look at a vector, it's a vector of complex numbers, and that forms the foundational math that you need in order to understand quantum computing. And most computer science programs do not include those classes, and some universities don't even have classes to introduce the math that is necessary. But you can pretty much study on your own. There are textbooks out there that can help you. And the other thing is you have access to Gemini. And Gemini does a pretty good job with that. Um, since we're kind of a little bit off topic on that one, I will point out one thing if that's where you want to, kind of the direction you want to go. Um, I think I have a little composite link to. Okay, let me just look for it. Understand? Nope, it's not here. Um, maybe not in this. Oh, there you go. Compilation of topics. Okay, so if you go to the very first link of the very first module and go to a really kind of obscure topic here, an example to understand something that is difficult and abstract, that is kind of a log of my own journey of understanding um, quantum computing. And there is an article or there is a text here that link to the source document. Okay, there you go. So you can click on this link. I'll open it in a new tab just so that we don't lose the original one. So, okay, site, nope, okay. So this link here, gives you the actual article that is written by a national lab. In other words, if you are a U.S. citizen or you pay taxes in the U.S., you paid for this already. Okay, which means don't feel bad downloading it and reading it for free because you just pay for it. But basically, this is a paper written by one of the national labs because they have so many people incoming not knowing enough about quantum computing. So the scientists decided, computer scientists, decided to write, an introduction to quantum computing um, for the employees, for the incoming employees. Okay, so I chose this as a topic to illustrate, how to understand something, because before this, I had no understanding whatsoever of quantum computing or the math, the foundational math that I needed to understand quantum computing. So I'm giving myself a project that has about the same difficulty as what you would encounter normally in a new STEM class so that I can kind of inspect my own way of studying and how I understand something. So this is my writing, but using that particular paper as a starting point so that I can go back to my own process of how to read something that's abstract and really kind of difficult to understand, and how I break it down to different steps and what I have to go through in order to understand, the original, whatever the paper is about. So if you're interested in this, okay, whether you're interested in quantum computing itself or the process by which I understand something, if you're only interested in the second, which means the cognitive process of understanding something, all you need to read are the things in the boxes. Okay, so I summarize the process itself and separating it from the actual thing that I was learning as an example. On the other hand, if you also want to learn quantum computing and want to learn the math behind quantum computing, you can read the entire thing. Or if you decide this is all mumbo jumbo, from the crazy professor like Tech, you can just not read it also. That's completely optional reading. Is that okay? You can also, kind of, push this to Gemini and say summarize. Yep, you're welcome. Alrighty. And we are back on topic. All right, so we are back on topic. This is all done. Okay, in other words, we are done talking about set related notations and operators. Okay, so from here on, we are going to make use of those definitions to understand more difficult concepts or more abstract concepts. Okay, all right, so let me go back to the Canvas shell, and I'm gonna, oh, you have a homework assignment. I almost forgot, and I'm forgetting to take row two. I'll do that in a few minutes. Um, right, homework assignment. So this is your homework assignment. It is just named your set notations. It is worth 10 points. You only have one attempt, okay? So for people who have taken some of my other classes where in the lab, I give people like infinite number of attempts. This one, you only got one, which basically means just don't click submit unless you're ready. You can start as soon as in about 20 minutes. Okay, I think I set the start time to be 1:30, so you can get started. You have a whole week, which means if you have questions about this, you can bring those questions to me on Monday, and we can talk about it. Okay, I probably won't give you an answer, okay, to the question itself. Most likely than not, I will answer your question with even more questions. That's typically how I answer questions. Um, but it does give you that opportunity, right? Yes. Say again. Let's take a look at it. I can't hear you. Sorry. Yes. Well, you can submit all the way to the you can not click submit until the very end of the period. Yeah, you can. Okay, you can spend. It's more than 120 hours between now and the due date. It's almost 184 minus an hour and 30 minutes. But you can find all the information that you need down here. The due date is at noon next Wednesday. So you got a week, basically. Hmm? Say again? You can start looking at it at 1:30. um, you know, you only get, this is for you to kind of ponder, right? You look at all the questions and go like, okay, how do I answer this question? You have to think about it. Now, can do I really want to catch people using AI to answer the questions? The answer is no. It is too much work for me. I'm not going to do that. Okay. But I can say one thing is people who spend the time to actually understand the concepts to answer the question, they typically would do much better in the exams. And in the exams, it's all paper and pencil. So there won't be any availability of AI in the exams. So you kind of have to think about the long-term thing and you just kind of evaluate your options. So with that said, I am going to take roll. Okay, so I will just kind of quickly turn on the roll taking activity so that we can do that. Okay, today is the 28th, so this is the one. I have to make some adjustments first because I uh, changed the time and I have to change the time to 1:20. Okay, so there we go. Do. Um, that's the access code, Optimus, and the time. You cannot do it yet because the end time is not set correctly. So I just have to do this 1:20 p.m. Click that. It is already published. You should be able to access it. And once again, the access code is Optimus. All right. So, um, well, I guess you guys can continue to do this when I move on to the next topic because today is a Wednesday, so you got a few days to study or at least pre-read for the next class. So I want to show you what we'll be talking about next. Let me turn on view as a student or view as student because that will give you a general idea of how to find. So what is Tech going to talk about next other than the off-topic stuff? So the next topic is going to be in the next module, which is about functions. So the next topic is function as sets, and then after that, we'll talk about injection, surjection, and bijection. So those are the notes that you probably want to at least get a chance to read. If you're busy, which I understand, at least upload the notes to Gemini or some other AI tool and ask for a summary. Because just a summary is already helpful in terms of just priming your mind so that you have a general idea of what we'll be talking about. Yes, the big operators. I don't need to go through it right now. If you have read it already, that's cool, but we are not. We don't quite need to use it right now, but we'll be using it later. Um, so I guess we can use the remaining time to kind of talk a little bit about it. Okay. Um, and I will use the whiteboard just for that purpose because the notes is a little bit too much, okay, in the sense, okay. So does everybody understand this notation? Okay, so I'm gonna just put here to we'll make it a very concrete thing, okay. And I'm just gonna say, I um Okay, we'll just do I. Okay, we'll just make it very simple. Okay. So does everybody understand the sigma notation, also known as the summation notation, right? But how do you explain that concept to somebody else? You can just go like, well, set this up as a loop. The loop starts with I being 0, it ends with I being 7, and then for each loop, evaluate whatever expression is here, whatever value it gives you, add it to the running sum, and that's the definition. Okay? I think that's okay, as an explanation of the sigma notation. So what I'm going to do is to think of this in a recursive way. Okay, this is also why CISP 440 and CISP 430 are linked, because I use a lot of recursion to explain concepts. And CISP 430, which is data structure, also uses a lot of recursion to specify how to get things done. So if I were to look at this and say, well, we can single out the 0, and then we just add the 0 to the sigma where I starts from 1 this time and it goes to 7. Okay, would that be a good way to look at it? Does that look recursive to you? Okay, no. What if I generalize? Okay, what if I say instead of 0, I use B for beginning, instead of a 7, I use E as an end, and so this becomes B. This is now B plus 1. This is now E. Does that look recursive to you now? Okay. But we already know that it has to end at some point, right? So the question is, how do we specify this is going to end? Okay. So the way we specify this is going to end is to use a ternary expression. Okay. So the ternary expression is something like this. Okay. And instead of using I, I'm just going to use f of I for some kind of a function, okay, just so that it's generalized, okay? So this is, okay, now here is the ternary expression. If B is less than or equal to E, okay, then we have this thing here, which is B plus, oh, nope, not B anymore, because we have f of B plus sigma I equals B plus 1 to E f of I, okay? So now the question is, what about the colon? Okay, what about the else value? What if B is greater than E? What if the beginning is greater than the end? You just use the identity of addition. Put a 0 there. Does that make sense to you? So that means if you go with this recursive definition, um, the beginning point of the sigma is going to increase. At some point, it's going to exceed the ending point. By that time, you just go like, oh, that's the end of the recursion. I'm just going to return the identity of addition. Does everybody understand what I mean when I said the identity of addition? It means 0 plus whatever is just whatever. Okay, so 0 is the identity of addition. Is that okay? So why use this definition when you can verbally and intuitively describe it like what I just did earlier? Yep, yep, there are no two ways to interpret this. Whereas the earlier description is kind of vague. I think you guys know it, okay? And that's why it's okay with you, because you already knew what sigma is representing. So that's why as long as it's consistent with my understanding, it's all good. But if this is the first time you're exposed to the concept of sigma, it takes a little bit of time to explain, okay? So this is actually the general idea of the big operator module is to look at all the so-called big operator, because sigma is what we call a big operator. We apply that operator across a range of things. Okay. Um, so that's kind of the whole idea of you know that whole discussion. So that's it. I'm not going to charge you guys for the extra minute of this class. I'll see all of you next Monday. Have a nice weekend. And don't forget the homework, okay? And try to read ahead of me. Even if you use the help of AI, do it.